Hello, everyone. Can everybody hear me okay? Okay, great. Thank you for having me. Today, I'm going to be telling you about the work I've been doing during my postdoc about electron irradiation of water ice covered silicon. So to give a little bit of context, our motivation for this work is to really understand oxidation and in turn oxygen isotope exchange between volatiles and substrates under astrophysical conditions, such as permanently shadowed regions of the moon, dust grains in the early solar system, and anomalous distribution of oxygen isotopes in the solar system. So the work I'm specifically doing follows the work of my advisor, Dr. Dominguez at CSUSM, where they found anomalous oxygen isotope exchange via electron irradiation of water ice covered surfaces, which can be seen in the figure on the slide. So what I'm currently trying to understand is the variability and magnitude of this oxygen isotope exchange. But in order to do that, we're using atomic force microscopy-based infrared spectroscopy, or AFM-IR, kind of similar to the last talk, but with infrared. And for these experiments, we're typically using silicon as the substrate, so we can clearly observe the formation of silicon-oxygen bonds, not oxygen isotopes. I'm not going to be talking about those today. So we run these experiments at the Isotope Characterization Experiment, or ICE Lab, CSUSM. We use silicon discs as our substrates, which are attached to a cryostat arm that is set to about 10 Kelvin, and then it's locked in an ultra-high vacuum. We use standardized water ejected into an adjoining high vacuum line that is pointed directly at the sample, and then is deposited onto the surface of the sample. And we electron irradiate these experiments at 5 or 1 keV. So the experiments, and I'm going to try to explain this as well as possible because it can get a little confusing. But first, we started off with control experiments. So for these, we started off with seeing if water ice and irradiation need to simultaneously be present in order to get this oxidation. So we did water only, where under the same conditions as all the other experiments, we deposited water, left it there for a while without any irradiation. Then we had irradiation only, where we just irradiated the sample and no water ice was deposited onto the surface. So after those, we have our actual experiments that incorporate both water ice and irradiation. We have two versions. We have the point where water is deposited onto the surface of the sample, and then it is irradiated. Those are called pre-samples. And then we have the post-samples, are where we irradiated the surface of the sample, and then water ice was deposited afterwards. So we had a nice little window in the paper so we could actually see what was going on during these experiments. And for these images that I'm showing you now, these are just the pre-experiment. So water ice was deposited and then irradiated. So if I can point this correctly, we have just images at the start, the middle, and the end of the experiments. Main things to note is that the beam is supposed to cover the entire surface of the sample. So imagine that. But then as we see, as time goes on, you can start kind of seeing like these openings or a dissipation of the water ice over time. That was something we didn't expect, and we think it's because there might just be a hot spot in our beam that may have happened over time. Sadly, it was not used over COVID, so maybe something happened. But we take note of it and make it apparent, and we talk about the results. And then also something important to note is how the water ice is distributed on the sample once it's deposited. Here we can see it's not a nice, clean, homogeneous surface. There are lots of tiny ice crystals, making it kind of heterogeneous. Or sometimes it just doesn't reach the entire surface of the sample, which is why it's really important to take images during the experiment so we can have that context. So after the experiments, we use the AFM-IR. Now, I don't have a lot of time to go into this, but the important things to note is that using AFM-IR, we get nanometer spatial resolution, and we get high sensitivity to surface chemical composition. So we're really kind of getting the spatial information that we need, understanding how heterogeneous the surface is after oxidation. So with the AFM-IR, we look at different locations across the surface of the sample, and at each location, we produce height and infrared amplitude maps, and then we also take point spectra. So to start off, I'm going to be showing you some of the standards and the controls that we did. First off, we have our silicon standard at the bottom, and that was a silicon disc that we took from the same original wafer as all of the other experiments. that was stored in a desiccator under vacuum. We also have one that was stored at atmosphere, just a drawer in the lab to see if it naturally oxidized over time. We had that irradiation only and water only experiments that I told you about before. And then we also looked at a silicon and an SiO2 grading to give us context as to where we should be looking for the silicon oxygen bond peak, which is dominantly around 1100. So I'm going to start off by showing you the 5 keV experiments that we did. This is looking at the blue spectra are the ones where the water was deposited and then the sample was irradiated. The orange is the post sample where the sample was irradiated and then the water was deposited afterwards. And so the main things to take away from this is that as we added or increased the amount of water, we seem to get a higher silicon oxygen bond peak at this 1100 wave number. And then when we look at the post 25 microliter sample, we do see that we get a signal, which is great, but we do see it's less of a signal compared to its pre-counterpart. And then we also have the 1 keV experiments, where for these, we just did 25 microliters of water going off of what we found in 5 keV. But here we can see that with the 1 keV experiments, we do get a lot less signal compared to the 5 keV, but we do notice that there is some level of oxidation that occurred. So overall from these experiments, the most important things to take away is that as we increase the amount of water that is on the surface of these samples during irradiation, we get greater amplitudes or greater silicon oxygen bond signal. And that we also find that the higher the energy, the more signal that we get. And we also notice that when water ice is deposited before irradiation, meaning they're both simultaneously present during irradiation, we also get greater amplitudes. And so in order to put this into context to really understand the surface heterogeneity that might be going on, I decided to show you, give context to the locations of where we took this point spectra on the surface of the sample. So this is a representation of the 5 keV post 25 experiment that we did. And so the markers do not represent the size or the area that we looked at. It just gives you a location. The markers are big enough so that you can tell what color they are. And so the colors represent that peak at 1100, so that maximum peak amplitude at that location. So what's interesting about this experiment is that we can see kind of a clustering of warmer colors towards the center of the sample and like bluer or cooler tones closer to the edge, representing that we get higher amplitudes really in a concentrated area, which coincidentally corresponds to that hotspot you were seeing in the earlier images of the experiments, which is represented by this dashed circle. And so that was just one experiment. Here's the other experiments that we did. It was that same type of pattern or representation. So these colors are the similar way where the warmer are higher amplitudes, bluer, cooler, but each of these examples is on their own scale, so it doesn't really put them in context to one another. But overall, just looking at them individually, we can see that the oxidation across the surface of the samples is much more heterogeneous compared to this one that I showed you on the last slide. And what we believe this is indicative of is that with these pre-samples, the water ice was getting in the way of the radiation. So it almost in effect, the water ice kind of in a way homogenized the heterogeneity of the beam, if that makes sense. But I wanted to be able to put these into context of each other. So these maximum peaks, we took the natural log of and set them all to the same scale. So what this does, you're able to still see the heterogeneity in each experiment, but it really highlights that we're getting a lot more signal from the 5 keV experiments compared to the 1 keV. So what I really want you to take away from this is that the electron irradiation of water ice covered silicon shows that oxidation and therefore oxygen isotope exchange occurs under various astrophysical conditions. We found that both water ice and irradiation are needed. And that for these particular experiments, oxidation heterogeneity could likely be due to the hotspot in our beam, but also likely due to the uneven water ice deposition, just because that's the nature of depositing it. Thank you.